Alright, thanks for watching, and today I want to prove an absolutely shocking result, namely that even though Z has holes, it actually doesn't have any holes. It's almost like a glass half full, glass half empty kind of thing. In other words, what I want to show you today is that the space Z is complete. In other words, every Cauchy sequence in Z converges. And why is that true? Well, suppose you have a sequence of integers that eventually gets closer and closer to each other. Well, the only way integers can be closer and closer to each other is if they're the same one. And think about this. Suppose I tell you two integers at most 1/2 apart. The only integers that satisfy those are the ones that are the same. And therefore, because of this property, any Cauchy sequence in the integers is eventually constant and therefore converges. And this is what we want to make completely rigorous now. So let Sn be a Cauchy sequence in Z. Then just apply the definition of Cauchy with, let's say, epsilon equals 1. What do you know? There is a threshold, capital N, such that after that threshold, we have that, let's say, Sn minus Sm is less than 1. But here's the thing, this is true for all capital M. So in particular, let M be capital N plus 1. Then what do we get? For all n bigger than capital N, we have that Sn minus S capital N plus 1 is less than 1. But what does that mean? Remember, if two integers are less than 1 apart, it means that they're the same. So for all n bigger than capital N, we have that Sn is equal to S capital N plus 1. But then what does the sequence look like? Again, before capital N, it can just be complete gibberish. But after capital N, all the values are just S capital N plus 1. And this sequence converges. Therefore, Sn, which is S1, S2, S capital N, S capital N plus 1, S capital N plus 1, S capital N plus 1, converges because it's eventually constant. To S capital N plus 1. And then they were done. Therefore, every Cauchy sequence in the integers converges. All right, thank you very much.